let's talk about ideal gases. Air. What is it anyway? We tend to forget that it's there. That is, until we need it. The air around us is made of a bunch of molecules, constantly moving around us and pushing against us. You might think there's nothing interesting to learn about something we rarely see or think about, but a long time ago, people got curious. One of these people, Boyle, learned about an important relationship. We can check this out in my liminal space, but let me go clean it up a little bit first. Alright, let's take a look inside my box, and let's look at a bunch of air molecules. And freeze. We can think about our air molecules as little particles bouncing around in a box. The number of particles is representative of amount in moles, the space in the box is the volume of the container, the speed of the particles, also known as their average kinetic energy, is the temperature, and the rate of the particles hitting the walls of the container is the pressure the gas is exerting. Now let's take a look at what would happen if we were to mess with some of these qualities. For example, what would happen if we decrease the volume? As you can see, the particles are hitting the walls of the container far more often, also known as an increase in pressure. The relationship between volume and pressure is explained by Boyle's law. As it turns out, Boyle actually had very little to do with the empirical discoveries that were used to form this idea, but he wrote about and published it first, so his name kind of stuck. As was discovered, pressure and volume are inversely proportional. As volume decreases, pressure increases. We can see that by plotting pressure and inverse volume, that is, 1 over volume, the relationship is linear. This tells us that at a constant temperature and number of moles, pressure times volume is equal to a constant. Another guy, Jacques Charles, wondered what would happen to volume if you adjusted the temperature, like in a balloon. Let's see what happens. We can see that volume and temperature are directly proportional. As temperature increased, so did volume. This is shown in the plot V equals T times K, which tells us that when pressure and moles are constant, V divided by T is equal to a constant. This is Amadeus Avogadro. Not only did he come up with the value for the number of molecules in a mole, which makes stoichiometry so much fun, he investigated the relationship between moles of gas and volume in a container. Take a look at this balloon. As air molecules go in, the volume of the balloon increases. This relationship is Avogadro's law, which, like Charles' law, shows a direct relationship. The number of moles of gas is proportional to the volume of the container, which is demonstrated on the plot. What's more, we can see that volume divided by moles is equal to a constant. This last guy, Joseph Gay-Lussac, often gets overlooked since we have enough information from the other 3 laws we've discussed. Still, he did an important investigation too, the relationship between pressure and temperature. As these molecules heat up and speed up, they hit the walls of the container more often, increasing the pressure the gas exerts. This is another direct relationship, as P is directly proportional to T. This also means that P divided by T is equal to a constant. Thanks, gas molecules. Now let's try and bring it all together. Okay, so we're just going to take a look at our data sets from our plots. Looking at Boyle's, Charles, and Avogadro's law, we have all of our data laid out right here. I've swapped around the equation here so that we have V on the left just to match the form of the other two. So what we're going to be talking about is what is KB, KC, KA, I called it KI here. And one of the most important factors is these other two variables were held constant for each of these. So for Boyle's, temperature and mole amount were held constant. For Charles, pressure and mole amount were held constant. And for Avogadro, pressure and temperature were held constant. So those are going to factor into that Ka, Kb, Kc, and kind of the difference between them will be those constant factors. So how can we solve for this value? So we can see that this is basically in the y equals mx linear form, and that's how it fits to our data points. So we can just solve it like we're solving for the slope. So I went ahead and solved each of these just using the first and last data point from each of them as our y2, y1, x2, x1. And notice I inverted those to match the form of the equation there. And so we found those values. So if we're accounting for p, t, v, and n being constant in one case or another, we can determine a fifth factor that connects all of these variables. So taking each, these are all the right sides of the equations here, we're multiplying them by each other, and so that essentially is multiplying v times v times v. So we get something in the form nt over p times each of their constants equals v cubed. And we're going to want to separate it out so that we have just one of each on one side, and v becomes something of a constant in this situation. And we're calling that r just being our universal gas constant that relates p, v, n, and t. So what value of v can we use on that right side so that it is like a constant? So what we did is we took one of these values. I used 1 atm because that was constant in both Charles and Avogadro. That being our constant value that will link together the other ones so that we can find that value of v. So just multiplying it by the slope, essentially, that k value we found that 489.1 milliliters was the volume value for 1 atm just based on Boyle's law. Then we used that to see what temperature that would be. That was 298 K, which does match what we had constant in the other ones. And then we found that it was 20 millimoles, which is also what we had constant in the other ones. So that 489.1 milliliters will work for the right side of our equation. So plugging those numbers in, just right there, we can cancel these out such that we will have this right here will turn into milliliters cubed, and then over millimole Kelvin, and also that ATM right there. So milliliter ATM, and then we can cancel that milli. So we'll get, oh, and then the milliliter squared here will cancel out at the bottom. So we'll have liters times ATMs times moles Kelvin, and that's where we get the units for our ideal gas constant, at least one form of it, which is 0.08206 liters times ATM per mole Kelvin. And we can use that to determine the relationship between all of these different factors in other examples. It's important to talk about the difference between ideal gases and real gases. So the ideal gas law is an approximation. It allows us to make educated guesses about the behavior of real gases in certain circumstances. Most importantly, real gases behave like ideal gases at high temperatures and low pressures. Ideal gases, the particles have no volume, the collisions are elastic, and there are no attractive or repulsive forces between the particles, and especially no reactions. With real gases, particles do have volume, energy is lost in collisions, and intermolecular forces are possible. However, at those specific high temperature, low pressure circumstances, the real gases behave enough like the ideal gases that the ideal gas law is a good approximation of real gas behavior. The ideal gas law can be used to find any one of the four variables if we're given the other three. So in this example, we're given N, T, and P. So our missing value, V, we can find by rearranging the ideal gas law equation into nRT over P. And from our last section, we know that R is equal to 0.08206 liters times atmospheres divided by mole Kelvin. So we're going to need to transfer this 11 degrees Celsius into Kelvin so that it will cancel out with our R value. So it's going to be 11 plus 273 is equal to 284 Kelvin. So we can go ahead and plug these values in. So volume is going to be equal to N 0.400 mole times R, which is this value here, times T, which is 284, divided by the pressure, which is 2.43 atmospheres. So let's go ahead and cancel out our units. So this mole is going to cancel there, Kelvin's going to cancel there. Oh, I forgot to write ATM, but it's going to cancel there. And that will leave us with liters, which is the correct unit for volume. And so if we plug that into the calculator, that's going to give us 3.84 liters as our volume in this given situation.